Combinatorics presented by Jamie Smith. Combinatorics is a branch of discrete mathematics which is essentially all about counting problems. In this session we will explore efficient ways of counting events by considering problems relating to arrangements, permutations, combinations and graph theory. A coin is flipped and an ordinary die is rolled. How many possible outcomes are there? Have a go at the problem and then unpause the video when you are ready. So let's have a look at a solution to this. We're going to use some GCSE theory here to help us. I'm going to draw a sample space diagram. Along the left-hand side of my table, I'm going to write the outcomes of the coin, heads and tails. Along the top of my table, I'm going to write the outcomes of the dice. So 1, 2, 3, 4, 5, and 6. And then using this sample space diagram, I can, of course, identify how many outcomes there are. So if I was to flip a head, I could then have 6 possible outcomes from my dice. And if I was to flip a tail, I could also have 6 possible outcomes, which would give me a grand total of 12 possible outcomes. Now, of course, I've counted them here, but that's not the most efficient way of doing things. I could have made this problem a little bit simpler for myself by saying, okay, well, there's a head and a tail. There's 2 possible things that can possibly happen. And with each of those 2 possible things, I can roll 6 different numbers on my dice. So I get 2 times 6, which is 12 possible outcomes. The fundamental counting principle states that if any event can occur in m ways, and after it happens in any one of these ways, a second event can occur in n ways, then both of the events together can occur in m times n ways. So referring back to our example, we had a coin which could occur in 2 different ways, and then following one of those 2 ways, we could roll a dice and the event could occur in 6 ways. So we had 2 times 6 equals 12 possible ways. How many different ways can the following be arranged in a line? The letters A, B and C, 10 unique objects, n unique objects. Pause the video, have a go thinking about the theory that we've already seen, and then unpause the video when you're ready to move on. We can answer the question of how many arrangements are there of the letters A, B and C by attacking the problem with brute strength. I can write out all the possible ways. So if I wrote them in alphabetical order as a logical starting point, A, B, C, and then keep the first letter fixed but swap the second 2 letters, I've now exhausted all the possible ways that I can start our 3-letter word with the letter A. So I'm going to move on to the next letter alphabetically, B, write the remaining letters out alphabetically, keeping everything nice and logical, and then I'm going to reverse the A and the C. And now I've exhausted all the words that can begin with the letter B. So then moving on to the letter C, writing the remaining letters in alphabetical order. I get C-A-B, and then switching the A and the B, so I get C-B-A, and I've exhausted all the words that could occur with the letter C. And so you can see here, we get an answer of 6. But the issue with combinatorics is you'll soon see that the number of ways that we can arrange items becomes a huge amount of ways, and it becomes very difficult to write them all out, making sure that we don't repeat any or miss any out, or just actually have the time to do so. It's inefficient. So we can think about this in a different way using the fundamental counting principle that we met a moment ago. If we imagine I've got 3 boxes, I'm going to fill each with one of the letters. We start off with that first letter, and there are 3 possible things that can happen. So there are 3 outcomes for that first box. Now, once I've chosen that first letter, for that second box, I've only got a choice of 2 remaining letters. And then for that third box, I've already picked 2, there's only 1 letter left. So I have 1 remaining thing that can possibly happen. And the fundamental counting principle means that for us to count how many ways this can all possibly happen, we multiply what can happen for the first box by what can happen for the second box by what can happen for the third box. And 3 times 2 times 1 equals 6. And we now have an efficient way of counting this. So how many different ways can we arrange 10 unique objects? Well, you're going to see now that this really is an example of where it is not manageable to write out all the possible ways we can arrange these objects. It's just not practical. So we're going to use that fundamental counting principle. Now, for my first object, I can pick 10 possible items. So there's 10 possible ways we can pick that first one. Now if I think about what can happen for my first two, so for my second object, I've already used one of the unique objects, so I have 9 remaining. So we get 10 times 9 possible ways those first two can happen. And then we get my third object. So we've picked 2, that's 8 remaining objects. And I'm just going to keep on going until I've picked my 10 objects. So there's my fourth. I've picked 3, there are 7 remaining. It's my fifth, I've picked 4, so there are 6 remaining. My sixth, I've picked 5, so there are 5 remaining. Seventh, I've picked 6, so there are 4 remaining. Eighth, I've picked 7, so there are 3 remaining. Ninth, I've picked 8, so there are 2 remaining. And then finally my 10th, and I've picked 9 others, there is 1 remaining. So I get the product of 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1, which if you do in your calculator is 3,628,800. And you can see by this point, even with a small problem like this, the number of ways that we can write out these unique objects is unmanageable to do so by brute strength. Now we can extend this idea to deal with n unique objects. We can't even write out one arrangement of n unique objects because n, of course, is a hypothetical amount of objects. However, we can write an expression that represents the number of ways that we can arrange n unique objects. So for that first item, again, using the same idea, how many different ways can we pick that first object? Well, there's n unique objects, so there are n different ways. And then I'm going to multiply it by the number of ways that we can have this second object. Now, if I started with n, and I've used one of those objects, what I have is n minus 1 objects left. And then I can go to my third object. At this point, I've already picked 2 objects out, so I've got n minus 2 objects left, so n minus 2 ways that they can happen. And what we'd do is we'd keep on counting, and we'd count all the way down to, we'd get the n minus 1th, there would be 2 objects left, and then the nth and final object that we need to arrange would be that very last one that's left. And so we get the product of all the integers from n down to 1. There is a way that we can write this in mathematics in shorthand. You may have met this. This is an n with an exclamation mark. N factorial. N exclamation mark denotes n factorial, the product of all the integers from 1 to n. So as you can see, counting down n times n minus 1 times n minus 2, all the way down to times 3 times 2 times 1. We can write it the other way around, 1 times 2 times 3, all the way up to n. It doesn't really matter, but the way we work with these counting problems, often it's better to write it in reverse, and it helps us solve some problems. The number of ways to arrange n distinct objects in a line is n factorial. So now you can take any number of objects, and you can calculate how many different ways you can arrange them in a line by calculating n factorial. How many different ways can the following be arranged in a line? The letters A, and B, the letters in the word madam, the letters in the word statistics. Pause the video, use the theory that we've already discussed to try and help you, and see if you can answer these problems. So let's arrange the letters A, and B. I'm going to do this by brute strength first of all, and then build up some theory from this idea. So, writing things in alphabetical order is a logical place to start. I could have A, B. And then swapping some letters around, I could have A, B, A. And then swapping that B again, I could have A, B, A. And then finally, I could have B, A. So there are 4 possible ways that we could do this. Now, as you already probably suspect, this isn't going to be a practical way to do all problems because the number of ways that we're going to write these items is going to soon become a large amount of numbers and it will be unmanageable. So we need a theoretical way to deal with this. Now, the way to go with this is let's just start off by considering how many ways could I arrange 4 unique items. And we already know 4 unique items would be equal to 4 factorial. So 4 times 3 times 2 times 1, which is 24. Now, the reason we've got 4 arrangements instead of 24 is because the letter A is repeated it's repeated 3 times. Now, if we imagine we considered these as unique items, A1, A2, A3, at the moment when we're describing them as unique items, they count as 3 separate arrangements. However, when we count them as non-unique items, so just the letter A, A1 equals A2 equals A3 is the same as writing A3, A2, A1. Because we're not paying attention to the unique A letters, we're just looking at the fact that they are the letter A. So, what we need to do here is we need to somehow discount all the arrangements that we would get if we thought of A1, A2 and A3 as unique items. So to arrange 3 unique items, we know is 3 factorial. So 6 ways. So what's essentially happening here is we start off with the arrangement of 4 unique items of 24 of them. And then because 3 of them are repeated, we are going to divide that 24 by the 6 ways that we can arrange the 3 repeated items, and I get an answer of 4. Okay, so quickly recapping, what we do is initially we can consider the problem as just arranging the unique items, and then what we do is we divide that arrangement of unique items by the number of ways that we can arrange the repeated items. Let's have a look at how that can apply in this example. The letters in the word madam, we want to rearrange these. Now you can see we've got 2 M's and 2 A's. This of course is a palindrome, another word that's the same backwards as it is forwards. That's neither here nor there, just a point of fact. But what we've got here are 2 repeated letters. So 5 unique items. So let's just consider, let's imagine all the letters are different for whatever reason. I would get 5 factorial, which is 5 times 4 times 8 times 2 times 1, which is 120. So if these were all different letters, there would be 120 different ways of arranging it. However, arranging the letters M and M, so that's going to be 2 factorial ways that I could arrange them, which is 1 times 2, which is 2. And arranging the letters A and A, also 2 letters, so there's 2 different ways of arranging them. So what we're going to do is we're going to take the arrangement of the 120 unique items, and I'm going to divide it by the 2 different ways that I can arrange the M and the M, and I'm going to divide it by the 2 different ways that I can arrange the A and the A. So I get 120 over 4, which gives me 30 different ways that we can arrange the letters in the word madam. Of course, once you start to identify this, we don't necessarily need to break the problem down like this. We can just step to a solution of 5 over 2 factorial. 2 factorial. Okay, so let's see if we can pull these ideas together now and write out the letters in the word statistics. How many different arrangements can we do? If you want to have a go yourself, you can pause the video, but we're going to do a solution now. So statistics. Statistics has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters in that word. So we know initially there are 10 factorial ways of arranging 10 unique letters. Now we know that we don't actually have 10 unique letters here. We have some repetitions. So for example, I have the letter S. I can arrange, there are 3 of them. So I need to divide through by the 3 factorial ways that I could arrange those 3 S's. If we look a little bit further, we've got the letter T. There's 3 T's in there. So I'm also going to divide by through the 3 factorial ways that I can arrange the letter T. We can also see we've got 2 I's in there. So I'm now going to divide through by the 2 factorial ways that I can arrange the letter I. And then the remaining letters, A and C, they're just single letters, so I don't need to worry about them. They don't affect our initial solution. Now when you go through this, we get 10 factorial over 3 factorial over 3 factorial over 2 factorial. Now, a little tip, so I thought I'd save it for this one, so you can have a look to see how you can do this without a calculator potentially. We could write this out and try and simplify things. So in some scenarios, you will be without a calculator. So if we write this all out, 3 times 2 times 1, so it's 10 factorial. If I divide it by 3 factorial, and divide it by this other 3 factorial, and then divide it by the 2 factorial, what we can do is we can start to cancel factors. I could cancel a factor of 2 times 1. I can also cancel a factor of 3 times 2 times 1, which is 6. We're cancelling out this 6. And then I've got other factors of 3 and 2, so what I'll do is I'll cancel those 3's, and then I'll cancel this 2 with a 4, and that would leave a 2 remaining. So if I was doing this without a calculator, and I think, to be honest, I'll have to do it with a calculator in the end, we would end up with 10 times 9 times 8 times 7. The 6 was cancelled, get times 5. The 2 is not cancelled, so we get 10 times 9 times 8 times 7 times 5 times 2. Now, I would use a calculator for that, but just wanted to give you an idea so you can simplify and try some of these simpler ones without a calculator, like in a UKMT or a MAT problem. We get the answer 50,400. Again, a really large number of ways that we can arrange these letters. The number of ways of arranging n items of which p are alike, q are alike, and r are alike, etc. is n factorial over p factorial times q factorial times r factorial, etc. So just to annotate and explain what we had there, remember this is arranging the n unique items. So we consider that first of all, and then underneath we divide through by arrangements of repeated or duplicate, let's call it duplicate items, arrangements of duplicate objects. How many different bracelets can be made using the following coloured beads? 1 red, 1 blue, 1 green and 1 yellow, or 3 red, 1 blue and 1 green, or 1 red, 2 blue, 3 green and 4 yellow. Okay, so just to help you out and give you a start with this one, because I'd like you to have a go and see whether you can have a go with this yourself using the theory we've already seen. What we're thinking about here is we are going to arrange 4 beads onto a bracelet, something like this. Okay, and you've got to think about whether they're unique or non-unique. So I'll give you a second to have a think about that and have an attempt, and then we'll look at the solution. Pause the video when you're ready to see a solution. Okay, so we're going to look at arranging 1 red, 1 blue, 1 green and 1 yellow bead on a bracelet. Again, we're going to do this by brute strength initially and then look at ways at how we can simplify this. So if I start off, here's my bracelet. We've got 4 beads, and there's something that we really need to consider before we do this. If I was to have red, blue, green and yellow, that's one way of writing it out. Now what we need to be clear on here is that if I was to arrange these beads as follows, red, blue, green and yellow, these 2 bracelets are exactly the same, as are the next 2 bracelets. So we'd have red, blue, green, yellow. The order clockwise is the same in every one of these arrangements. And this is what poses a problem. This is what makes this a little bit more difficult. Oops, that shouldn't be blue. It should in fact be red. We should have red, blue, green, yellow. We've got these 4 seemingly different arrangements. Actually, they're exactly the same, because if you start with the red and read round clockwise, the remaining colours are all organised in the same way. So this is what we do. We cut out that problem of being able to rotate the positions in the clockwise direction by fixing one of the beads. So instead, if I was to say, write this out, and say, okay, well, I'm going to fix the red here, and that red is always going to stay there. I've then got 3 unique items to arrange in any way I want to, and it doesn't matter because we've now fixed this bracelet. I can now think of the remaining 3 as in a line. So what we get, and I mean, what you could think about this, if you're not quite clear what that means, then I could now think about this as a bracelet that's unwrapped like this, where we're always going to count from that red bead clockwise. So that means that I can now say, okay, well, how many can I pick for my second bead? Well, there's 3 beads remaining, times how many for my third bead, which is 2 beads remaining, times how many beads for my second one, or for my last one, sorry, there's 1 bead remaining. So there are 6 different ways. And actually what we can do every time is when we deal with these problems each time, we can start off by thinking that, okay, we've got to fix one of these beads. And then once I fix one of those beads, there are 1 less bead to arrange, which essentially we're going to arrange in a line. So I can then fall back on what we've done previously with fundamental counting principle and just do the number of beads take away 1 factorial. So let's now try and apply that to this theory. And we'll back up the answer with a diagram afterwards. What we're going to do is we're just going to consider, first of all, that I've got 5 beads here. Okay, because you can see I've got that repeated 3 blue beads. So let's just imagine I've got 5 beads. So in a ring, we are going to get, instead of thinking about arranging 5 beads, what we're going to do is we're going to fix one of those beads. It doesn't matter which bead it is. And then we're going to consider writing it out in a line. So that means it's going to leave me 1 less bead than the 5 that I've got. So 5 minus 1 factorial, or 4 factorial. 1 times 2 times 3 times 4 is 24. Now, if I was making a bracelet with 5 unique beads, there would be 24 different ways. But again, we've got this idea where I've got my 3 blue. I've got my repeated blues. And what we've already seen is if something's repeated, what we want to do is we want to divide through and cancel out the number of combinations created by writing those 3 beads and thinking of them as 3 individual beads. Instead of thinking of them as blue 1, blue 2, blue 3, we're just going to think of them as blue, blue, blue. So what we're going to say is, okay, well, let's say arrange 3 blues. We know is 3 factorial, which is 6. So our arrangements for our beads is going to be equal to the 24 if they were unique, divide through by the 6 due to the repetition that we won't get, and I get an answer of 4 different arrangements. And actually we can see that, and I'll show you grammatically quite quickly how we can do this. Okay, so looking at our diagram, let's imagine I've got 5 places, 5 beads to fill. I'm going to focus on the blue because that's a repeated colour, and I'm just going to put a blue here. And what I'm going to do is I'm going to put the 3 blues next to each other. Okay, so I've got my 3 blues next to each other. And what I can do then is the 1 red and the 1 yellow, I could write red there and yellow there, or if I was to write it out again, what we're going to have is the blue, 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 and then yellow, red. Now, of course, I could rotate these around. I could have the blues across the bottom, etc., but we're not doing that. We're remaining fixed. So let's think about this slightly differently. Now let's do it where the blues are not together. Okay. So if the blues are not together, I'd have to fill in one of these other positions, one of these bottom 2. So I'll fill in one of those 2 blues there. And now I've got 2 spots that I can, or 3 spots left that I can put a blue. I could put a blue in between these 2 here, but I'm not going to because that means I get 3 blues in a row again. Or I could put my blue over here or down here. It doesn't really matter. But the simple point here is that actually there's only 2 ways that we can write these blues. We can write them in a group of 3, or we can write them in a group of 2 and a single 1. It's the only way we can split them up. And so when I come to the remaining beads, as you're probably expecting, I get a red there and a yellow there. Or the only other way that I can do this now is by pairing the two blues together, and then I've got 5 beads, and what I want to do is I want to put the blue in the same position in the bottom right, and then I'm going to swap the yellow and the red, and that's our 4 solution as. Okay, because there's only 2 different ways that we can group those blues. We can group them as a 3, or we can group them as a 2 and a 1. If I wanted to group them singly, I would need to have a gap in between each one, so I'd need 6 beads. So finally, let's extend this to this final problem. In this problem, we want to arrange 1 red, 2 blue, 3 green, and 4 yellow. So we're going to speed this up a little bit more, and we're just going to go straight to an answer using our factorials. Now, what I know here is that there's a total of 10 beads. So, using the theory when we got this bracelet, we're going to have to fix one of those beads so that we've got a starting point. It doesn't matter which one, but what it means is we fix one of those beads, and that means I've got 9 remaining. So the total possible things that could happen for 10 unique beads would be 9 factorial. Now I need to divide through by those repetitions, the number of ways we can write the repetitions. So starting with the 2 blue, there would be 2 factorial ways of ordering the 2 blue. There would be 3 factorial ways of organising the 3 green. And then there would be 4 factorial ways of ordering the 4 yellow beads. And again, this time I'll show you a little bit of cancelling again. We'll see how we do with the numbers as to whether I do it on a calculator. But just remember, for non-calculated techniques, what you're going to want to do is, once you know what you're doing with the factorial, you've written it out, write out the actual factorials and start to cancel common factorials. So I get 2 times 1 times 3 times 2 times 1 times 4 times 3 times 2 times 1. So straight away in this case, I'm going to cancel off the largest factorial, 4 times 3 times 2 times 1. And that leaves me with quite a small amount. 3 times 2 times 1 gives me 6. And then I've got factor of 2, so put that in there. And what we've simplified this to is 9 times 2 times 7 times 5. So I'd get 18 times 35, which you could do with long multiplication, and you get an answer of 1,260 possible different ways. The number of ways of arranging n objects in a ring where p are alike, q are alike, and r are alike, etc., where clockwise and anti-clockwise arrangements are different, is n minus 1 factorial over p factorial, q factorial, r factorial, all in a product. So remember, this top is arranging n unique items in a ring, and then in the bottom we divide by number of arrangements of the duplicate objects. Okay, now notice we talked about where clockwise and anti-clockwise arrangements are different. So just to help you with that, what we mean by this is if we was to have 4 objects where we'd number 1, 2, 3, 4, what we're saying is if you count that clockwise as 1, 2, 3, 4, that is different to this arrangement here, in which 1, 2, 3, 4. We're saying that these two are different. Okay, you can see that they're basically mirror images of each other. We get the number 1, 2, 3, 4, depending on whether we read clockwise or anti-clockwise. And at the moment, what we're doing is we're distinguishing between the both, saying, okay, we're just reading clockwise, and that's how we count our unique arrangements. Some problems want to count clockwise and anti-clockwise as the same, so that they don't really mind which way round we're going. And so to deal with the situation where we have n objects in a ring where p are alike, q are alike, and r are alike, where there's clockwise and anti-clockwise arrangements are the same, you can see it's n factorial over 2 times. So we've just added in this 2 times. And the reason we're dividing through by the 2, just reminding you, the n minus 1 factorial is to arrange n unique items in a ring. And then the p factorial times q factorial times r factorial comes through from dividing by number of arrangements of duplicate items. And the reason we get this divide 2, going back to what we saw a moment ago, if I have these 4 objects, 1, 2, 3, 4, what we're doing is I am counting this as a duplicate, 1, 2, 3, 4. So instead of having these 2 arrangements, I've now got 1 arrangement. Because we're saying clockwise or anti-clockwise, we don't really care which way we follow the line. And so we halve the number of arrangements again. So half arrangements, counting clockwise as the same as anti-clockwise. A running club runs an annual cross-country race in which different age groups compete for their ranking. Find the following number of different rankings for each age group. Top 3 positions from 10 runners, top 6 positions from 30 runners, top R positions from N runners. Have I got a problem thinking about the previous problems that we've already discussed? And when you're ready, press play to see the solutions. Okay, so we've got a running club and we're looking at its annual cross-country race in which the different age groups are going to compete for a ranking. So we want to find the following number of different rankings for each age group. So if we are looking at first, second and third, we want to see how many different ways from the 10 different runners, first, second and third, could occur. And so what we want to think about is actually there are 3 positions. There is first, second and third. And so the number of people who could come first would be 10 runners. And if one person has already come first, there would be 9 runners left who could come second. And if there are already a runner in first and a runner in second, that means that there are 8 possible runners left who could come in third. And so the number of different rankings would be the product of this, just like we've been using from the fundamental counting principle. And so we get an answer of 720. Now, I'm going to do something a little bit unusual on this at this point because we've got the answer and all we've done is just reuse the logic that we've done earlier. But I'm going to show you something that's going to be a little unusual at the moment, but it's hopefully going to help you with something we're going to do a little bit later on. So if you imagine my solution here was 10 times 9 times 8, and we've been working with factorials. So what I'm going to do is I'm just going to extend this so that I can write this as 10 factorial. Times 3 times 2 times 1. Now obviously if I was to do 10 factorial here, then it wouldn't give me the answer of 720. But what I can do is I can, very much like an equivalent fraction, if I multiply the top by 7 factorial and the bottom of a fraction by 7 factorial, so I've got this factor of 7 factorial that will cancel. Apologies, let's correct that a second. So I've got 7 times 6 times 5 times 4 times 3 times 2 times 1. Now if you imagine that this was the sum I started off with and I cancelled the 7 factorial in the denominator and the numerator, that would leave me with 10 times 9 times 8 times, which gave us our answer. So actually what we can do is we can write our answer that we've just given and we calculated using our first principle logic as 10 factorial divided by 7 factorial. And that's going to be useful later on. Now again, if you haven't already had a go, pause and have an attempt and see if you can get this one right. Otherwise, I'm going to push on now with the solution. So we want to do pretty much exactly the same question, except this time we want the top 6 positions from 30 runners. So again, if I was thinking about first, second, third, fourth, fifth, and sixth, we're just going to modify that counting principle and think, okay, well, the number of people who could come first would be 30. I'm then going to multiply that by the number of people who could come second. One person has come first, so that leaves 29 for second. I'm then going to multiply that by the number of people who could come third. So we've already had 2 people finish in first and second, so I've got 28 left. And then multiply that by the number of people who could come fourth, so 3 people have come from first to third. So we've got 27 left. And essentially, we're just doing what we did before, except we're not counting all the way back down to 1. We are counting down just enough to go back to the number of positions which we require. In this case, 6 positions. So the top 6 positions from 30 runners can be calculated by doing 20 times 29 times 28 times 27 times 26 times 25, which is going to give us a huge number, much bigger than any numbers we've got so far, 427,518,000. Now, let's think about this problem again. Similarly to what I did a moment ago, if we imagine writing this as 30 times 29 times 28 times 27 times 26 times 25 times 24, and I'm just going to fill in the rest now. Actually, I'll use a different colour for this bit here. So that's from our answer. And so then if I extend it so I can write 30 factorial, 24 times 23, and I'm not going to do all of it because there's simply not enough space, times 2 times 1. Now, because I've added this additional, multiplied by this additional 24 factorial in the numerator, I'm going to do exactly the same in the bottom, so I'm going to have 24 times 23 times ... all the way down to times 2 times 1. Now what we're doing, imagine is the stuff that the factorial in red has actually been cancelled out. And the reason I'm doing that is because what that means is my answer to my question I could write instead as 30 factorial, which is written out in the numerator, divide by that 24 factorial that's in the denominator. And what that does is the 24 factorial in the numerator and the denominator cancels to leave that sum that calculates the number of positions in the first 6 places. Okay, so if you haven't done so already, have a go at this problem now, thinking about what we've done in the last 2 questions. Pause it. When you're ready to have a look through and see if you've got the right answer, then restart the video. Okay, so we're going to look at the top R positions from n runners. So in other words, what we're going to do here is we're going to look at first, second, third, all the way up to R minus 1 and rth. So, in first position, we could have n runners, times by the number of runners that could come in second, so that's 1 less than the n runners, times by the number of people that could come in third, which is 2 less. And if you notice the pattern that we've got here, it's n minus 1 less than the position. So in first position, we had n minus, instead of 1 less than 1 is 0, so n minus 0. In second position, we've got n minus 1, which is the same as having taken away 1 from the 2 in the second. In third, we get n minus 2, and that n minus, that number is 1 less than the position. So what we would have in this case is, in the rth position, we would have n minus r minus 1 minus 1. And then in our rth position, we just have n minus r minus 1. Now we could tidy this up. I could write this as n minus r plus 2 times by n minus r plus 1. And that's really all we can do and leave it to write it as an expression. But what I could do, and really what we were trying to do, and what I was trying to aim to do in those previous 2 examples, was this isn't a very nice expression. This isn't a simple way to write things out. So what I can do is I can use the ideas that we did from our last last two examples to get to a point where we have like a formula, a simpler way of expressing this. So I've got the n times n minus 1 times n minus 2, and this will go down all the way down to n minus r plus 1. Now what I want to do is I want to extend the numerator of our fraction so that it becomes n factorial. So I'm then going to multiply by n minus r, because I'm going to take away 1, and then I'm going to multiply by n minus r minus 1. And then it's going to multiply all the way down to 2, and then finally 1. And what we've got to remember to do is whatever I've done in the numerator of my fraction, I want to remember to do in the denominator of my fraction. So what I have in red here is all the integers from 1 up to n minus r multiplied together. So n minus r, which in a moment I can write as n minus r factorial. And again, the stuff in the writing in red, imagine, is the part of a fraction that I can cancel, because what I'm looking to do is write this answer to my question in a simpler way. And so my numerator is n factorial. So what we do is we imagine just actually, in fact, instead of ordering r objects, we just imagine, okay, let's order the n objects, all of them. And then what I do is I cancel off the factorial of the n minus r objects that I'm not going to arrange. So we get n factorial over n minus r factorial. So the number of permutations of R objects chosen from n, where order is important, is given as npr, where we get n factorial over n minus r factorial. And that's what we was answering in those previous questions. How many arrays can we arrange R objects from a set of n, where the order is important? So remember, what we're doing there is we're taking note of who is in first, who is in second, and who is in third. This is different to some other problems. A running club runs an annual cross-country race in which different age groups compete to qualify for the club's national cross-country team. Find the following number of different teams for each age group if the teams are formed from A, the top 3 positions from 10 runners, B, the top 6 positions from 30 runners, and C, the top R positions from n runners. Now, what you have to be careful of here is this question looks almost identical to the previous question. In the previous question, we was looking to see how many different rankings we had. Now, in rankings, the order is important, so we want to know the difference between what position Alice is in, or what position Bob is in, or what position Chris is in. When we're picking a team of runners, we're just looking at the people who finish in the top 3, or the people who finish in the top 6. So we don't really care the order in which they come in, just want to know how many different groups of 3 or groups of 6 will come from that number of runners. So think about what we've done all through this video so far, and then have a go at the question. Pause the video, and then when you're ready, press play to see the solutions. So what we're going to do now is we're going to find a number of different teams that we can form if we're going to pick the top 3 positions from 10 runners. Now, what we've already seen is that we could calculate the top 3 rankings by imagining that we're going to calculate how many ways we could order those 10 runners, and then, because I'm not interested in the last 7 runners, divide through by the number of ways I can order those last 7 runners. Now, that gave us an answer of 720. But actually, what we want to pay attention here is that when we make this team, if we imagine we've got Alice, Bethan and Claire are in the top 3 positions, I don't care what order Alice, Bethan and Claire comes in. Now, Alice, Bethan and Claire could come in Alice, Bethan, Claire, Alice, Claire, Bethan, Bethan, Alice, Claire, Bethan, Claire, Alice, or Claire, Alice, Bethan, Claire, Bethan, Alice. 6 different ways. In fact, every set of 3 runners could be organised in 6 different ways, because we know with groups of 3, that's 3 factorial ways that I could organise them. So actually, our team that we want to pick. We don't care whether Alice, Bethan or Claire comes first, second, third. We're just interested in that group of 3. So what we're going to do is we're going to take that 10 factorial, because we want to know how many ways can I order the 10 runners. I'm then going to divide by the 7 factorial because I'm only interested in those first 3 runners. And then I'm going to divide by the number of ways that I can organise those 3 runners, because I don't care what order they come in. And this will tell me how many different teams. So what we found here, we'd get the 720 divided by the 6, which would give me 120. That's essentially what we're doing from first principles. Now I can do it, write it out as factorials. If I show you how we would calculate that without a calculator, just to give some tips for those non-calculator papers, we'd write out the 10 factorial over the 7 factorial and then multiplied by the 3 factorial. So initially, cancel 7 factorial as the largest factorial in both the numerator and denominator. So cancelling through, there's a factor of 1. They just cancels out directly. I can cancel a factor of 3 in the 9, so leave a 3. I can cancel a factor of 2 in the 8 to give me 4. So this multiplication ends up as 10 times 3 times 4, which is 120. Now, if you want to pause and have a go at the next problem, thinking about what we've done here, please do that now. So this problem is very similar to the previous one. This time we want to do the top 6 positions from 30 runners. So I'm going to build it up using the first principles. We know the number of teams. First of all, we can consider how many ways can I organise the 30 runners. I can organise them 30 or arrange them 30 factorial ways. Now, I don't actually want to organise or arrange all 30 runners. I'm only interested in the first 6. So what I'm going to do is I'm going to divide by the number of ways that we can arrange the last 24. So that just tells me now how many different rankings could we have in first to 6th. And that's what we worked out in our previous example. But I don't want to pay attention to the rankings because I'm going to have 6 runners. I don't care who comes in first, second, third, fourth, fifth or 6th. I'm only interested in who are those first 6 runners to cross the line. And so what I do is I divide by the number of ways I organise that group of 6 runners, which is 6 factorial. So the number of teams will be given by 30 factorial, divided by 24 factorial, divided by 6 factorial. Now, an even quicker way to cancel this out and write it out, and I will end up using a calculator, but just to kind of help you speed up when you're working without a calculator, I know that I'm going to cancel the 24 factorial. So in fact, on the top, all I'm going to write is 30 times 29 times 28 times 27 times 26 times 25. I'm going to count back 6 positions and write that out, and then I'm going to multiply by 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. And so then I could go about cancelling through factors. 6 times 5 cancels with the 30. We can do 4s into 28 gives me 7. 3s into the 29 gives me 9. 2s into the 26 gives me 13. And then I could go about multiplying it. Now this is quite a large number, so in all honesty I'm going to use a calculator here. But it's just to help you see how the ways we can cancel and simplify these. So we get 593,775. Okay, so if you haven't already had a go at this one, or if you're thinking now that perhaps you're going to get a different answer, have a go at this question, pause the video, and then in a moment I'll go through the solution. Press play when you're ready to see that. So this time we want to find out how many teams there are, where we're going to pick the team from the top R positions from the N runners. And I'm just going to build it up through all those first principles that we've seen previously. The number of teams is going to be equal to, well, first of all, I'm going to consider how many different positions could N runners make. And that's N factorial. Now, I'm not interested in N factorial position arrangements because really, I don't want the last N minus R positions. So I divide by the N minus R. Now remember, at this point, what I've actually got is the number of permutations. This will tell me the number of ways, the number of different rankings So remember, rankings where order is important. This tells me the number of rankings I can have of R people from N. Now, since I'm picking a team, I don't really care about that ranking. All I care about is the first R people to cross the line. What I'm going to do is I'm going to divide by the number of ways I can arrange R people, which is R factorial, and that will cancel through that factor of rearranging R people R factorial times. And so the number of teams that we can make from a group of N runners, where we're going to make it from the top R positions, is N factorial over N minus R factorial times R factorial. So the number of combinations of R objects chosen from N, where order is unimportant, is given as N factorial over R factorial times N minus R factorial. And the thing to note here is when we're doing permutations, we only divide by the N minus R factorial because we're interested in the number of different ways that we can actually organise those R objects. Where order is unimportant, we divide through by this factor of R factorial to remove and to cancel the number of ways that we can actually order those R objects. So they're very similar formally. They're very easy to get muddled up potentially. But if we think about the first principles, how we actually formed these formula, hopefully you should remember and be able to use them in the correct context. So, just some important guidance on using some of these ideas. When you're considering the combinations of an event A and an event B together, the important word being and here, what we want to do is we want to multiply the number of combinations of events. So if you remember when we had a coin flipped and a dice rolled, what we did was we multiplied the number of ways that the coin could come up by the number of ways that the dice could come up, because we're saying flip a coin and roll a dice. If we was considering the number of combinations of an event A or an event B, then what we do is then we add the combinations. And this is very similar. It's linked to probably your first kind of real introduction into tree diagrams, etc., where you had the and rule and the or rule. Just be careful when we're doing our next problems. If you have 5 objects of being chosen, and 3 of which are chosen from a specific group, you have to remember and consider how you're going to choose the remaining 2 objects. And this will become a little bit clearer in a later problem. And one of the key things to keep in mind when you're doing some of the later problems is when you are looking at groups of objects and how they are grouped, sometimes we can rethink how they're organised in order to help make problems easier. So like when you're choosing from red, blue and white objects, you could simply think of that set of objects as blue and non-blue objects. This will become a little bit clearer as we come on to a later problem. Just a quick reminder of the basic definition of how we calculate probability. Probability problems involving combinations can be solved using the definition of probability for equally likely events. So what we know from the very first kind of lesson we ever have on probability is the probability of an event A is equal to the number of ways event A can occur over the total number of outcomes. So thinking about rolling a dice, what's the probability of rolling an odd number? Well, there's 3 ways of rolling an odd number, 1, 3 or 5, and it's a total outcomes of 6, so it's 3 over 6 or a half. The letters of the word mathematics are written one on each of 11 separate cards and laid out in a line. Calculate the probability that each pair of letters are placed next to each other. So all we're going to do here is you're going to use all the theory that we've covered to calculate a probability using the basic definition of probability. So pause the video, have a go. Once you think you've got an answer, press play and have a look at the solution. The letters of the word mathematics are written one on each of 11 separate cards and laid out in a line. Calculate the probability that a pair of letters are placed next to each other. Well, the first thing I'm going to do in this problem, I'm thinking about definition of probability, in which I want to know how many different ways can we organise the letters of the word mathematics so that the M's are paired, the A's are paired and the T's are paired. And I want to write that over the total number of ways that we can organise the letters in the word mathematics. So I'm going to go for the total number of ways, total number of outcomes first of all. total outcomes. So what I'm talking about here is I'm talking about arrangements. I'm looking at how do I arrange those 11 letters, how many different ways can we arrange them. So what we know from previously is that if I'm going to arrange 11 unique items, that's going to be 11 factorial. But what I know is that I've got non-unique items, so I want to divide by the number of ways that I can organise each of those sets of non-unique items. So for example, M. There are two M's, so I can organise them 2 factorial ways. So I'm going to divide that out of our unique combinations. I've got the letter A is in there twice. So again, I'm going to divide by another 2 factorial. The letter T is in there twice. So again, I'm going to divide by a factor of 2 factorial. Now, the remaining letters, H, E, I, C, and S, are all unique. So what I've done is I've treated it initially, like we saw earlier, as our 11 unique items, but then divided through by the number of ways I could organise each group of similar items. So 11 factorial over 2 factorial times 2 factorial times 2 factorial. I'm not going to write this out. We'll calculate that using a calculator because it's a large number. You could have, of course, used some cancelling techniques like I did earlier, but in this case, we're going to get 4,989,600. And so probably a little bit too much to do manually. Now, what I know is these are all the possible outcomes when I rearrange those letters in the word mathematics. What I now need to know is how many different ways that I can do that, where the M's are paired up, where the A's are paired up, and where the T's are paired up. Now, the way to think about this now is actually, if I have to pair the M and the M together, I could think of it as if they are one letter paired as a double M. Similarly, I could think of the A and the A together as one letter because they have to be paired together. And finally, I could think about the T and the T together because they have to be paired together. And so I've got this one pair of M's, this one pair of A's, and this one pair of T's, which I'm treating as single individual characters because they have to be paired together. And then I've got a H, an E, an I, a C, and an S. So actually, number of ways written as pairs, written as pairs. Now, because I've written the double N, the double A, and the double T as a unique single character, or at least that's how I consider it, all I have to do is, what's the number of ways this can be written as pairs? So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8 factorial. And there are no repeats. So 8 factorial, which when we calculate that on a calculator will give you 40,320. So the probability they are written pairs together is going to be the number of ways that we could write out the mathematics with the letters paired together over the total number of ways that we could write out the word mathematics. So 40,320 over 4,989,600. And if you put that on your calculator, you can actually cancel that, and that will simplify to 4 over 495. And there's your probability. So really nothing new there. It's just using the theory that we've gone through and looking at the theory in order to build up and count the number of ways that we can achieve different events in order to satisfy some conditions. A local council consists of 8 Conservative, 6 Labour and 4 Plaid Cymru councillors. A subcommittee of 4 councillors is formed. Calculate the probability that the subcommittee contains A, all Conservatives, B, 2 Conservatives, 1 Labour and 1 Plaid Cymru, C, mostly Labour. So, just to give you a clue before you attempt this, is just to remind you that if you're picking a subcommittee, a team of 4, then you don't really care who you pick first, second, third and fourth. You just care about who is in that group. So have a go at the question. Once you've had a go, press play on the video and see the solution. Okay, so we've got this local council. It consists of 8 Conservatives, 6 Labour and 4 Plaid Cymru councillors, and we're going to pick a subcommittee of 4 councillors. And we want to know the probability that that subcommittee contains all Conservatives. So again, we're going to use our basic definition of probability. We're going to think about the total outcomes, the number, and then the number of ways that we can pick a team made of all Conservatives, and then we can calculate the probability. So let's start with the number of ways we can pick all Conservatives. So number of ways pick 4 Conservatives. Okay, so now the order is unimportant of picking those 4 Conservatives. So what I'm thinking about here is I've got a total of 8 Conservatives and I want to pick 4 Conservatives. So I'm just going to use combinations because the order isn't important. I'm going to do 8 choose 4, which would be, if we're doing it longhand, 8 factorial over r factorial, which is the 4. And then we're going to do 8 take away 4, which is 4 factorial. And a quick tip, the numerator, the digits in the numerator will always add up to give you the digit in the numerator. So if we did 8 factorial over 4 factorial times 4 factorial, that would give us the number of ways that we can pick 4 Conservatives from 8, which is 70. Total number of ways to pick a subcommittee. So just picking a subcommittee, we don't care what party they come from. So what we're going to do here is we're going to have our total of, there are 8 plus 6, which is 14, plus 4, which is 18. There are a total of 18 different people that we can pick our council subcommittee from, and I'm going to pick 4, so I'm going to do 8 choose 4. And again, the order isn't important here, so I'm not doing permutations. I'm not interested who I pick first, second, third, or fourth. So we're going to get 18 factorial over the number of people we picked, which is 4 factorial, and then 18 take away the 4 gives me 14 factorial. And when you calculate that, again, I use a calculator just for time at this point, we're going to get 3060. So the probability of all Conservatives will in fact be 70 over 3060, which you can actually cancel to 7 over 306. So that's how we could approach that problem. In general, we wouldn't probably break it down into different stages. I'm just trying to make things a little bit clearer for us at this early stage. In the next one, we're going to try and step a little bit closer to an answer. Okay. So if you haven't already had a go at this one, or you're thinking that perhaps you need to correct your first attempt based on that last answer, please have a quick go at that now. Pause the video and then press play when you're ready to see the solution. So in this problem, we want to calculate the probability that the subcommittee is made up of 2 Conservatives, 1 Labour and 1 Plaid Cymru. Okay, so what we're going to do is we're going to say probability, and I'm just going to initialise them. We're going to have 2 Conservatives, 1 Labour, 1 Plaid Cymru. So it's going to be the number of ways teams, or number of teams which are 2 Conservative, 1 Labour, 1 Plaid Cymru, over the total number of teams. Now, we've already calculated the total number of teams. That was calculated by taking the 18 councillors and choosing 4. Now what we want to do is calculate the number of teams that would contain 2 Conservatives and 1 Labour and 1 Plaid Cymru. Now, why am I accentuating the Plaid Cymru? Well, sorry, not the Plaid Cymru, the and. Well, if we think about this, I'm going to pick my team of 4. First of all, I have to pick 2 Conservatives from a total of 8. So I'd do 8 choose 2. I'd have to pick 1 Labour from a total of 6, so I'd do 6 choose 1. And I'd also have to pick 1 Plaid Cymru from a selection of 4, so 4 choose 1. Now, because I want to have 8 Conservatives, and, sorry, not 8 Conservatives, I want to have 2 Conservatives, and I want to have 1 Labour, and I want to have 1 Plaid Cymru, what I'm going to do is I'm going to multiply all these possible outcomes. Now, when you work through this, if you calculate the total number of teams which contain two Conservatives, one Labour and one Plaid Cymru, you will get 672 teams. We already know that the total number of teams we could pick was 3,060, and this would then cancel to 56 over 255. In this last problem, we want to calculate the probability that the subcommittee contains mostly Labour. Now, what that means is we could pick a team that has either 3 Labour in or 4 Labour in. And what's also important here is that we don't care whether we pick a Conservative or Plaid Cymru, we just care that those remaining councillors are non-Labour. So actually we can help make this problem a little bit simpler by thinking of this as a set of 6 Labour and 12 non-Labour. And you'll see how that helps in a moment. Okay, so the probability of mostly Labour would be equal to the probability of 3 Labour or 4 Labour. Now, the or is important here because I'm saying one thing can happen or another thing can happen. So I'm going to total up, I'm going to add, I'm going to sum those probabilities. So what we're going to say is, okay, probability of 3 Labour plus the probability of 4 Labour. Okay, so the probability of 3 Labour. Now what I know what I'm going to do is I've got 6 Labour councillors and I'm going to choose 3 of them. So that tells me how many ways I can pick 3 Labour councillors. But I've got to remember I've got to pick a 4th and final council member. Now, easiest way of doing this is just saying, okay, well there's 12 other members who are not Labour and I'm going to pick one of those. And this is all going to be over the number of teams which I can pick, which is 18, choose 4. And then I can add the probability of the number of ways I can pick the probability of 4 Labour. So that would be, I've got 6 Labour councillors to pick from. I'm going to pick 4. That's all 4 picked, so I don't need to worry about anything else. And then I'm going to divide that by the total number of teams. Alternatively, I could have written this out slightly differently. I could have just put this all over a total of 18, choose 4. And I could have taken the number of ways we can pick 3 Labour, 6, choose 3, times 12, choose 1, and just added it to the number of ways I could pick the 4 Labour. Now, if I was to do that, the total number of teams I could pick that was mostly Labour would be 255. This is over the total number of teams I could pick, which was 3,060. And if you cancel that down, you get 1/12. So a slightly different problem this time, getting into some simple graph theory. The problem here is moving only right and down. How many different paths are there from A to B? So have a go at the question and pause while you're doing so, have the video paused, and then restart the video when you're ready to see the solution. Okay, so the easiest way to do this is to perhaps have a look at this by brute strength. And we're only going to do this to start off with, just so we can see what we could do, and then we'll look at a shortcut. So I've got 8 routes up here because I believe that there's 8 paths, and the way to do this, we can see, if I do it logically, going across the row, that's my first path. And then if I continue along that top one as much as possible and then come down 2 instead, that's my second path. This time if I just come across 1 and then go to the furthest point, that's our third path. This time if I come across 1 and then only come across 1 on the second bit, that's my 4th pass. If I come across 1 and then down 2 and across, we should see we've got 5 paths. Now if I come down and then work all the way across, that's my 6th pass. If I come down straight away and come across just 2 before coming down again, I get my 7th pass. And then if I come down at my first opportunity, then at my first opportunity again and all the way across, you'll see we get 8 routes. Now that's all well and good. This is a fairly simplistic problem and it doesn't take too long to do, and if you're careful you won't miss or you won't duplicate any routes. But there's got to be a simpler way to do that. So this is what's called a binostat. You may have seen one of these. Basically, a ball is dropped in this entrance here, and as you can see, it drops down, hitting the pegs, and falls into different end results down at the bottom here. You may be familiar with this. You may be more familiar with the theoretical idea, which is Pascal's triangle, which is closely linked to the binomial theorem and binomial probabilities. Now, we're not going to touch too much on that. I'm just going to use some ideas from Pascal's triangle to help us solve these problems. So, if you imagine we're going to drop a ball into our binostat, and imagine it's just going to drop and there's one end position it can go. Well, if I drop the ball in there, there's one way it can get in here, that's through that point that it's dropped through. Not very interesting, not much to learn. So let's move on to if we're dealing with, okay, 2 rows of this binostat. Now, when it drops into that top box, it can either drop to the left, which means there's one way to get to this position on left, or it can drop to the right, which means that there's one way we can end up out in that far right position. And again, there's not very much interesting going on at this point. But as we get onto the next rows, you start to see it gets a little bit more interesting. So imagine now I'm going to drop the ball and it's going to go all the way down to this 3rd row of positions. I could come all the way down here, and there's only one way I can reach this outer left position. That's by keep on falling to the left. Similarly, if I wanted to reach the outer right position, there's only way that I can keep on doing that, and that's if every time I drop to the right. But this middle position is interesting because actually there's 2 different ways I can get there. I can come down to the left and then back to the right, or I could come down to the right and back to the left, which means that there is 2 possible ways to meet this original position, this middle position. Okay. So what about the 4th row? Well, again, if we start with the outer ones, in order to get to the far left, I'd have to keep on dropping left every single time. There's only one way I can get there. And to get out to the far right position, I'd have to keep on dropping right at every level. So there's only one way of getting there. But again, these middle 2 are interesting because I could either drop down to the left all the way and drop in, or I could come down to left 1 and into the position above and down, or I could drop to the right and then 2 to the left. Now, what's interesting about this is we get a total of 3. And that total of 3 comes from the fact that in the row above to the left, there's one way of getting to that position, and the row above to the right, there was 2 ways of getting there. So the total number of ways to get to that position in the middle is in fact just the sum of the 2 squares above it. So this becomes a 3. And again, there's 3 in this last position because there's 2 ways into the middle and 2 ways down to the right, and they add up to give you this position in the left. And this is Pascal's triangle. Once we see this pattern, it's fairly simple to complete. The next row, then each cell is going to be added up by the total of the cells above it. So on the outside left, we get 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And 1 plus nothing is 1. And this is what's interesting about Pascal's triangle. And if you notice when you look at that picture of the binostat, all the balls congregate around the middle. That's because it's more likely for them to fall into these middle positions because there are more roots into those middle positions. So again, if we go to the our 6th row now, the outer position, there's only one way to get there. So there's going to be very few times that that ball reaches that outermost position. Next one in is 5 different ways I can get there. So more balls will reach that position. Come in 1 again, there's 10 ways to get to those 2 middle positions. And then notice also it's symmetrical. So there's 5 to that almost most far right, and then 1 to the far right. And the reason on that initial image you saw that the balls were congregating in the middle is simply because there are more roots to those positions in the middle than there are to the outside. And this is Pascal's triangle. Well, Pascal's triangle is useful because we can use this to solve our problems. We can just tweak what we're doing here to help us with these path problems. So let's use Pascal's triangle to help us with this problem. If we start at point A, there's only one way to get to point A. That's because I start there. But now if I consider coming across There's only one way to get to my start point and only one way that I can move across this route here. So there's one way I can get to the next corner. Similarly, coming across, there's still only one way that I can get to this one corner. Okay, so we start going horizontally. Now let's go down vertically and do the next horizontal row. Now if I was to come down, there is only one possible way that I can get down to that bottom left corner. Here's where things start to change, like Pascal's triangle. If I'm to come across to this next corner now, there are two different routes which lead into it, each of which I can only get to by one way. So that means there's a total of two routes to that position. Okay, not too interested in this yet, but let's go work across horizontally. Leading into my next position, there are two ways that I can go into this next position horizontally and one way coming down vertically. That means a total of three ways to get to that point. And moving across, again, let's go horizontally. There's only one way that I can get to this final corner. There were three routes that lead into here, so there are three routes which lead to this far right corner. And then we've done our next horizontal. And we keep on going through, we're going to go through the whole maze, saying how many ways it takes to get to each point. So now dropping down vertically. There were two ways to get to the point above. There are no other ways to get down to this corner here, so there are only two ways to get down to this bottom left corner. So now, coming across to my next point, there are two routes leading into this point, one of which I could get to using two different routes, the other of which I could get to using three different routes. So I get a total of 5 routes to this penultimate point. And then finally to part B, there are two different routes leading into part B. One of the routes coming across horizontally, there are 5 ways of doing that. Coming down vertically, there are 3 ways of doing that. And that gives me my 8th route. And if you go back to the original diagram, what you'll see is that these will match up to, you can count through each one of those points, the routes I draw, to see how many pass through each of these points. And you'll see, for example, at this point here, out of all the routes that I drew, 3 of them will pass through this point. So this is our final problem. What we're being asked here, you're given a path or a graph, and it's asking what is the probability that a random path chosen from A to B, only moving right and left, passes through the point X. So what I want you to do is have a go at this problem using the theory that we've discussed. And then once you're ready to see the solution, press play on the video. Okay, so to calculate the probability a randomly chosen path from A to B, only moving left and right, passes through X, what we're going to do is we're going to say probability passes through X equals number of routes through X divided by the number of routes to B. Okay, so we're just going to go through and do this entire maze just as I did a moment ago. Okay, so I like to work from the point A. We're going to start with a 1 there and then work across horizontally, then come down a row and work across horizontally, etc. It's the most methodical way I find. So coming across the top, there's only one way, one path of 1 that leads to that middle top row. And similarly, there's only one route of 1 leading to that top right corner. So I now come down. Coming down to the point below, there's only one route to that one single point. But now as I come across to the right, there are 2 roads leading in, giving me a total of 2 routes, the 1 plus 1. Coming across 1 square to the right, I've got the 1 plus a 2, gives me 3. And then because I've got 1 route into each of these, there's only one possible way of getting across. We're just going to get that 3 plus nothing, 3 plus nothing, 3 plus nothing each time. So then I drop down a route, and as I drop down, there's only one way I could possibly come down to this bottom left corner. And then at my next point, I've got 1 route coming in horizontally, 2 routes coming in vertically, so that gives me 3. At my next point, I've got 3 routes coming across horizontally and 3 vertically, so that gives me 6. I then have 6 routes coming into the point for X horizontally, and 3 routes coming in from the point to the point X vertically, that gives me 9. And so what I now know is that there's a number of 9 routes going through X. Now we're just going to continue on. Point past x, there are 3 roots coming down vertically, 9 roots coming horizontally, so we get 12. And then the next one, 3 roots vertically and 12 roots horizontally, we get 15. So come down a row. Coming down from the 6, there's only one way you can do that, so we get a 6 again. But this time for our next point, I'm going to get the 6 plus the 9, which is 15. For my next point, I get 15 plus 12, which is 27. For my next point, I'm going to get the 27 plus 15, which is 42. And my next point, only one coming across, so we're just going to get 42 possible ways. So coming down a row, coming down, there's only one vertical line coming down to that. There's 6 ways to that point. So to my next point to the right, we've got 6 roots horizontally, 15 vertically. It's a total of 21. Our next point, 21 horizontally, 27 vertically, total of 48. Our next point, 48 horizontally and 42 vertically, gives us a total of 90. And then our final point on this row, we've got 90 coming in horizontally, 42 vertically, gives a total of 132 roots. And we're almost there. Just this final row now. So coming down to our bottom left corner, there's 48. And there's only one way coming down, so there's 48 into that bottom left corner. Coming across to the right, we get the 48 roots coming in horizontally, 90 roots coming in vertically. So I get a total of 138. And then my final point, I've got 138 roots coming in horizontally, and 132 roots coming in vertically. So we get a total of 270. So the total number of roots to be is over 270. And when you cancel this, we get a probability of 1 over 30. Okay, so I hope you found the video interesting and that you understood it and have maybe even enjoyed it. I hope that it gives you the start that you need to try on combinatorics problems. Combinatorics is a huge topic and it starts with some very simple problems and gets very complicated very quickly. So really what I've done today is just a taster of what is there for you. Now what I say to all my maths students for any topic that we cover is that don't forget YouTube is a treasure trove of resources and you can learn all sorts of things, including mathematics. So you can go onto YouTube and search combinatorics. There's lots of videos. Some are about kind of popular science, the backgrounds, the interesting ways combinatorics gets used in the world, and some you'll find are courses and lessons on it. One particular course I stumbled across was one on the combinatorics and discrete maths. It's a pretty comprehensive course. I had a look at 1 or 2 of the videos. I'll be honest, there's 30 of them and they range from about 10 minutes up to 30 minutes. So I haven't watched them all, but what I have done is I've had a quick look through the comments, which are very complimentary. And I've had a look at, scanned through a couple of points of some of the videos, and it seemed like a really good course of videos. Now it is verging from taking you from A level into kind of university level standard. So we'll take you far beyond what you need, but it's a really interesting course, a really interesting topic overall, and will give you more detail, more examples and more theory based on combinatorics. Really today is the tip of the iceberg.